Hello, and thanks for having me here today. We're going to talk about something a little bit different than we've been talking about here this afternoon. But look at solving one of hydrogen's biggest challenges, and that's going to be transportation. Right? We've all been there. You're late for a meeting. You're late for work. You pull up to a train crossing, and the whistle's going off. You got to stop. Queue up. Well, let's count the tanker cars, right? Let's go to the petroleum station, fill up, right? How many times have we had to maneuver around the petroleum truck that's dropping off some petrol? Or looked out your kitchen window and seen the heating oil truck show up, right? The Industrial Revolution, the 1850s, have brought us a lot of great things and a few not so great things, right? It's gotten a lot better. We are now refining, transporting, and using petroleum much cleaner. But you can't change the general chemistry fundamentals that you combust carbon materials, you produce CO2. And we need to get off that. Okay? So, what's next? Let's talk about hydrogen for a minute here. So, as Jeff just up here mentioned, right, we can make hydrogen from natural gas, right? Steam reforming in natural gas give you hydrogen, also gives you CO, and which will be oxidized further to CO2. And your heat, your energy, usually comes from petroleum-based energy there too. But you need hydrogen from the steam reforming. Lots of research is going on looking for clean ways to make hydrogen, and that's not what I'm here to talk to you about today, right? But the technology now to think about water-splitting electrolysis is becoming pretty mainstream and moving rapidly into a space where we can start thinking about this as an energy source, right? Splitting water, making hydrogen and oxygen. But just like petroleum, just like refining petroleum, we'll have to do these in localized areas. The technology will have to be scaled up to be made more economical, right? Which means we have to get the hydrogen from point A to point B, right? And where are we going to have to take this hydrogen, right? Thinking about fueling stations. There will probably be some hydrogen vehicles on the road that have to stop at a petroleum station or a petroleum-like station, right? Data centers want to think about using hydrogen fuel cells as their backup energy when the grid goes down. You have to get hydrogen there. Chemical plants will need hydrogen to make the molecules we need, from pharmaceuticals and agrochemicals and everything else. So we still need carbon-based molecules for. So what is next, right? So thinking about hydrogen as it's transported today. Tube trailers, transporting hydrogen in the gas form. You'd also think about liquid hydrogen, cooling hydrogen down so that we can now transport it in a liquid form. The energy it takes to bring hydrogen down to liquid temperatures and to maintain it at those temperatures is intensive, right? So let's think back. Let's go back to what we're doing now with petroleum. We run into this every day. We see it. We may not notice it. We see it. We have to think about this in a common route. How do we think about transporting energy? And let's think about it as volumetric densities. Volumetric density is easily defined as a specific quantity of unit of volume. It's reported in, say, kilograms per cubic meter. Cubic meter is 1,000 liters, about the same size as the volume of your washing machine in your house. Okay? So, volumetric density of hydrogen and petroleum. Let's look at these two. Hydrogen at ambient temperature and pressure. That's the temperature and pressure that's outside here today, right? 0.09 kilograms per liter. For petroleum, at ambient temperature and pressure, 800 kilograms per meter squared. Quite a bit different there, right? And how we can then transport much more petroleum and get more energy out of that transportation than we can for hydrogen. Okay, so gas phase hydrogen is far apart. Let's cool it. In order to cool hydrogen to liquid temperatures, it's got to be negative 425 degrees Fahrenheit. A lot of energy, a lot of thick-walled tankers to transport that, right? but we do get up to 71 kilograms per cubic meter, getting closer to that 800. So let's go back to gas phase hydrogen. And let's even go back to everybody's favorite subject of high school chemistry and the ideal gas law. Ideal gas law explains how pressure and volume can be related to the number of molecules in a closed system and temperature. Okay? Now, let's keep it isothermal. Let's not worry about temperature. And the gas constant's that. It's a constant. It doesn't change. Right? We still have to think about the volume and the pressure. And if we want to put more molecules of hydrogen in a tank, one of those needs to change. Right? The volume goes up, pressure goes up. One of those two have to happen. If you want to get more molecules of hydrogen in a tank, we've built an infrastructure. Interstates and roadways. We're not getting bigger tankers, right? The trains aren't pulling bigger tankers either. So let's go to pressure. Let's think about pressurizing hydrogen. I showed the picture earlier, the tube trailer. DOT limits the pressure that this can carry at 250 bars. 1 bar is equal to 1 atmosphere. What atmosphere is what it looks like outside in Florida right now at sea level. It's a little bit lower out here. Right? 250 bars can carry 380 kilograms of hydrogen. Okay, what's that mean? How do I think about that as a number I can relate to? Right? This is the Toyota Mirai, a hydrogen-powered fuel cell vehicle. Right? They have these up at NREL. Requires about 5 kilograms of hydrogen to travel about what you get out of a tank of petrol, 375 miles. Right? 1 tube trailer can fuel up to 76 of these cars. Okay? So, one of those, a Mirai is about the same size as a Toyota Corolla. But I can power 8. I can fill up 8 Toyota Corollas in 1 tank of petroleum. So, using gas phase and liquid phase hydrogen is going to be very challenging. Plus, we have an infrastructure that we've built and we spent trillions of dollars on based on petroleum. So how can we use that to transport hydrogen? And that's what we work on in my lab. Right? Liquid hydrogen carriers. The ability to chemically convert hydrogen to a petroleum molecule, transport it from A to B, and then pull that hydrogen off that molecule, and we can set this up in a cycle. This example here takes toluene. You hydrogenate toluene at the generation site of hydrogen. You put it on your shipping container, your truck, your train. It's methylcyclohexane when it's hydrogenated. This is a petroleum molecule. We use the infrastructure we have. On the other end, when you need to use the hydrogen, you do the dehydrogenation. Right? Liquid hydrogen carriers, there's a few of them. The one I just gave an example of is methylcyclohexane and toluene. Now we can think about hydrogen energy density, 47 kilograms per cubic meter, right? Not 800, but also not 0.09. Right? There's other ones too. Formic acid. Formic acid is hydrogen and CO2 reacted together, right? 53 kilograms per cubic meter. Ammonia, right? Ammonia, Fritz Haber, Karl Bosch, in the early 1900s, discovered how we can make ammonia to a point now where it's now the second most abundant chemical made on Earth. Right? We know how to transport ammonia. We may not know how to make it very well yet, but we're working on that too. Right? 107 kilograms per cubic meter. The challenge that we think about is this catalyst. How do we hydrogenate? That takes a catalyst. A palladium catalyst and heat will take your methylcyclohexane, dehydrogenate it to toluene, and the reverse. Now, where do we get our heat? Right? Combustion of carbon materials. What we do in my lab is start thinking about how we can get rid of that heat. And we're doing that thinking about light. And developing light catalysts that can convert light to thermal energy through plasmatics. This is actually a sample out of my lab. We use high surface area, porous, transparent materials to support catalysts. Palladium is a hydrogenation catalyst. It's been around for years, right? We throw some gold in there, and we put them close together. Now, all of a sudden, we can use light, energize it, and do hydrogenations and dehydrogenations. Formic acid, methylcyclohexane, and we haven't tried ammonia yet. For 17 decades, the petroleum has given us a lifestyle, innovation, and growth that we've all enjoyed. Right? But we have to start thinking about the next generation. We're working on how to make it, we're working on how to use it, but at the same time, we have to think about how we're going to transport it, or we're not going to be able to get the power where it needs to go. And thank you for your time today.